In this video, we're going to talk about ways that a function can fail to be differentiable. So recall the definition of the derivative. A function is differentiable at x equals c if the limit below exists and is finite. The limit as h goes to 0 of f of c plus h minus f of c divided by h. And in that case, we say that the derivative of f at c is equal to the value of that limit. So let's think about that limit in terms of situations when a function is discontinuous. So we know that one type of discontinuity is a jump discontinuity. And let's think about that limit above. So the limit as h goes to 0 of f of c plus h minus f of c divided by h. Well, here we see that this right here is f of c. But the limit in this case as h goes to 0 of f of c plus h does not exist. So that does not exist because if we look at the limit here, from one side the limit is f of c, but from the other side the limit as h approaches c for positive values of h, the limit is going to be something else, like say it's -1 or whatever, and +1 up here. So this limit does not exist, and since this limit does not exist, the overall limit, this whole limit, does not exist. So in this case, in the case of a jump discontinuity, f is not differentiable at a jump discontinuity. All right, what if we've got a removable discontinuity? So that's a place where there's a hole in the function, and either that hole is sort of plugged at a different point, or f of c just does not exist. Again, let's think about the limit as h goes to 0 of f of c plus h minus f of c divided by h. So in this case, the issue is that the limit does exist, but it is far away from f of c itself. So what we have is this is equal to the limit as h goes to 0 of whatever this limit is, let's call it L minus f of c divided by h. And this distance between L and f of c, L minus f of c, is greater than 0 because there is a discontinuity. If it was equal to 0, then it would be right there and there wouldn't be a hole. And so we have a constant over 0, some constant over 0 as h goes to 0, and this limit does not exist. So it could be positive infinity, could be negative infinity, but it is not a finite value. So again, we f not differentiable at a removable discontinuity either. What if there's an infinite discontinuity? Well, you may be sensing a pattern. It's not going to be differentiable here either. So limit as h goes to 0 of f of c plus h minus f of c divided by h. Well, now, first of all, f of c does not exist if we have a vertical asymptote. And that's enough to say that, if we can't even evaluate this, then that limit is just not going to exist. Not differentiable at c if there's a infinite discontinuity or a vertical asymptote. And similarly, if we have an oscillating discontinuity, so like sine of 1 over x was an example like this. That doesn't happen that often. But in that case, then the limit as h goes to 0 of f of c plus h does not exist. And so therefore, f is not differentiable at x equals c. In this case, it would be x equals 0. So all that is to say that if f of x is not continuous at x equals c, then f will also not be differentiable at x equals c. And that is something that I want you to know. That statement is logically equivalent to its contrapositive, which is this theorem right here. If f is not differentiable at x equals c, if f of x is differentiable at x equals c, then x will be continuous at x equals c. So let's prove this statement. So suppose that f is differentiable at x equals c, then the limit as h goes to 0 of f of c plus h minus f of c, all divided by h, exists and is finite. Okay, so what does that mean? So if that's the case, then since the limit as h goes to 0 of all of this exists and is finite, that means that the top must go to 0 as well. So this must go to 0 because this is going to 0. Otherwise, we'd have a non-zero value divided by 0, which is positive or negative infinity. So let's just say then, f of c plus h minus f of c must go to 0 as h goes to 0. And therefore, the limit as h goes to 0 of f of c plus h minus f of c is equal to 0, which implies that the limit as h goes to 0 of f of c plus h is f of c, if we just subtract c to the other side. And this is the definition of continuity. So the definition of continuity is that as x approaches c, or the limit as x approaches c of f of x is f of c. That was the definition of continuity, and we see that that's logically equivalent to h goes to 0, what does f of c plus h go to? So c plus h is our x. As x gets close to c, or as c plus h gets close to c, we have a limit of f of c. So therefore, if a function is differentiable at x equals c, then it will also be continuous at x equals c. And again, this is a statement I would like you to know. So is the converse true? If f of x is continuous at x equals c, will it necessarily be differentiable at x equals c? So I'd like you to pause and just think about this for a moment, and then we will talk about it. Okay, so in general, this is not true. And specifically, it can fail if there is a corner at C, or a cusp at C, or a vertical tangent line at C. So we're going to see each of those possibilities. So we'll first see that f of x is not differentiable at C if there's a corner at C. So here we have the function f of x equals absolute value of x, and here we have a corner at x equals 0. There's a corner here. And so let's think about this limit. So the limit as h goes to 0, here c is equal to 0, of f of 0 plus h, f of it is just absolute value of it, minus absolute value of 0, all divided by h. And so the issue is that as we approach from the right-hand side versus the left-hand side, we'll get a different limit. So let's look at the right-hand limit first. This is the limit as h goes to 0 from the right of, okay, what's the absolute value of 0 plus h? Well, anytime that we're going from the right, the absolute value of a positive number is just itself. So this is just h minus 0 over h. Now we can cancel those h's because it is not the value at h equals 0, but for values close. So this is just the limit as h goes to 0 from the right of 1 over 1, which is 1. Now what about the left-hand limit? So limit as h goes to 0 from the left. So that's 0 plus h minus 0 over h. And what's the absolute value of, something like negative 2? Well, it's positive 2, but h of, or the absolute value of x is equal to negative x for x less than 0. So we see that this output, negative 2, the output is a negative negative, a positive 2. And so this is the limit as h goes to 0 of negative h minus 0 over h, and that gives us a limit of -1 instead of 1. So these limits are not equal, and therefore the limit as h goes to 0 of this limit f of 0 plus h minus f of 0 all over h does not exist, and therefore f is not differentiable at x equals 0. But it is differentiable everywhere else. It's just not differentiable at that corner. So to describe that a little more intuitively, anytime there's a corner, then the limit as h goes to 0 of what should be the derivative will not exist because the left and right hand limits will not be equal. So, if we're talking about plus h for positive h's and plus h for h less than 0, for h greater than 0, then those two limits will not be equal. And we can see that when we just think about, what happens to the derivative as we're going this way. That's like the slope of this line. So the slope of this line is positive, 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 and then it's over here, it's negative, 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 and then there's this sharp turn where the derivative just does not exist. At c, the limit is not approaching one single value, so the limit overall does not exist, and the function is not differentiable at x equals c when there is a corner. Okay, so if f of x has a corner or a cusp at c, then f of x will not be differentiable at c. We've already talked about this situation. Now let's talk about when there's a cusp. At a corner, there is not one limit as h approaches 0 from the left and the right. At a cusp, like the one below, the slope of the tangent line will be positive or negative infinity. So the difference between a corner and a cusp takes place with a curve surrounding the point, whereas a corner is straight lines surrounding that point. So an example with a cusp would be this f of x equals the cube root of x squared. So now let's just see this with taking the derivative, not with limits, but the way that we kind of know. So the derivative with respect to x of x squared cube rooted, that's the same thing as x to the 2/3 power. So when we take that derivative, we'll get 2/3 x to the negative 1/3. And that's the same thing as 2 over 3 times the cube root of x. So where's the issue? We've got this cusp at x equals 0. What happens to the derivative when x equals 0? So what happens when x equals 0 to this derivative evaluated at x equals 0? That would give us 2 over 3 times the cube root of 0, and that of course does not exist. So we could also argue the same thing just using limits. The limits when we approach this way and the limit when we approach this way are not going to be equal. But we also see here that there is an issue of the derivative just clearly not existing for x equals 0. And anytime there's a cusp, the derivative won't exist at x equals 0. Lastly, if there's a vertical tangent line at x equals c, then the function will not be differentiable at x equals c. So here, just for like 1 second, the tangent line to this curve is infinite, or it has an infinite slope. Let's just see that working. Again, this is an issue at x equals 0. And when we take the derivative, f prime of x would be, so this is the same thing as x to the 1/3 power. So this is 1/3 x to the negative 2/3, and that's equal to 1 over 3 times the cube root of x squared, because the negative flips down the fraction. When we evaluate this at x equals 0, we see that this does not exist. We have a 0 in the denominator. So this would be a situation where for just a moment in time there is a vertical tangent line, and at that moment the function is not differentiable. So to summarize, a function fails to be differentiable at x equals c if any of the following are true. F of x is not continuous at x equals c for any reason: removable discontinuity, jump discontinuity, infinite discontinuity or asymptotes, or oscillating discontinuities. F of x has a corner or a cusp at x equals c, or f of x has a vertical tangent line at x equals c. In any of those situations, f of x will not be differentiable at the point x equals c.